layer to a drill that's completely out of position. It could be a rogue drill, or it could be the whole drill program is shifted. And then on the right hand side you can see there's so much shift it's actually breaking out. There's zero annular ring to be measured. So in this case these would be non-conforming. So this would typically be down to a shifted drill problem. And the same applies to microvaves. So we're trying basically to hit the center of the target land to make it reliable. So in this case you can see that it's slightly misaligned. We're not hitting sufficiently onto the target pad. So this would meet class 1 and 2, but it would not meet class 3. So we mentioned at the start of the presentation materials that the fabricator could be used in metal cores. So this could be a 30 mil or a 60 mil, either copper, brass or aluminum type material embedded inside the board itself. The challenge here is that these materials are typically drilled and filled with a resin system prior to lamination into the PCB itself. So again, this just adds another element of movement. So basically the position of these holes is critical to the actual fabrication or the lamination and the drilling process as well, to ensure that the drill actually hits dead center of these clearance holes. In some instances, for instance, it may be a copper core that could be direct connects. But in certain cases it's a clearance, so the designer has to ensure there's enough clearance or setback in case of any misalignment or drill movement. So if the clearance is tight and there's some misalignment out of the core or the drill, or there's a layer shift, obviously you want to ensure that there's sufficient clearance. And the concern is, even at 4 mil clearance, which would be acceptable, is if you had rough holes and wicking, it would be very easy to short that hole to that internal plane. If it's a power pin going down into here and this is a ground plane, you could develop a potential short. So please ensure that sufficient clearance is given between metal cores and the actual via themselves to allow for any or all process errors, all stacking in the wrong direction. And in worst case condition, the distance is too short, so there's a very high propensity that it's going to fail. Unfortunately, if it was this close, it would probably pass electrical test, but there's a chance it may fail in the life when it's out in the field. So microsection is critical to ensure that there's sufficient clearance and that one of the layers hasn't shifted, and that it could potentially cause an infantile or even a long-term failure when it's out in the field. So you can imagine these drills at these very high speeds. If the fabricator just drilled straight into the copper, it would cause excessive burring, like you would see here. So what he actually does is he uses special entry foils and backing materials to try and eliminate or reduce the amount of burring that actually occurs during the drilling process. So the next process is, even though he does that, he will experience a little bit of burr around the holes themselves. So what he's going to do is go through a deburr process, which is twofold. The first part of the process is to